from Chicago, will tell us about saddles and non-supersymmetric strings. Thank you.
Great. Yes, today I'm going to give you a 20-25 minute just brief discussion of some results that we found kind of surprising about non-supersymmetric strings recently. So let me start by thanking my collaborators on this project, who are Bernardo Freeman, Mariana Grania, and Hector Parra de Freitas, pictured below. And what I'm going to tell you about is work that should appear hopefully in the very near future, but that's always with some optimism about completion times. I'd also like to thank my collaborators on the earlier project from a few months ago, Zini Beikara, who used to be an undergraduate at Chicago and now is a graduate student at Harvard, and Daniel Robbins, my former student, as well as the organizers of this workshop for the opportunity to speak here. So here's an outline of my talk, and it's meant to be a very informal talk. Please feel free to just interrupt with questions and comments, if any. I'll start with some introduction about what the basic question is I want to address. And then I want to discuss something about the potential energy for the heterotic string in the simplest of all possible compactifications, just on a circle. And that's where we'll find most of the surprises already. And I'll close, assuming there's time, with an explanation about how you can embed this in ADS, this kind of story. All right, so let me start with an introduction. So classical string theory usually involves specifying a worldsheet conformal field theory. Actually, one second. Let me move this thing. Okay, there we go. As a first step. And such conformal field theories need not describe any geometry in the target space or even solutions of supergravity. We could have more general backgrounds described by Landau-Ginzburg theories and so on. However, we largely focus on examples that are solutions of supergravity, like R4 cross a Calabi-Yau or ADS5 cross S5. And in that context, it's easy to find supersymmetric Minkowski and ADS solutions. On the other hand, if we look around the universe, we see that there's a large component of dark energy, about 70% of the critical density, with a tiny scale compared to the Planck scale. And we need to explain how this could come about from string theory. So there are two leading proposals for this, for explaining dark energy. In the past, the most popular proposal was a landscape of metastable de Sitter vacua, just a very complicated potential with a caricatured below, with an enormous number of minima spread around. And one of those minima would correspond to us. And I asked DALI, just to get some AI input, to draw a picture of the string theory landscape, and it gave me this surreal picture, which I kind of like at the end. The second possibility is dynamical dark energy, and a version of this appears in the Swampland program under a conjecture called the refined de Sitter conjecture, which is an attempt to rule out de Sitter by imposing conditions on the structure of the potential that can come out of string theory. So there's a claim that if either the slope of the potential should be larger than order 1, or the shape of the potential should be upside down. And if this scenario is true, then you could never realize de Sitter. I mean, in string theory, de Sitter would reside in the swampland. And again, I asked DALI to generate an image of the swampland of theoretical physics, and it came up with this kind of interesting and somewhat disturbing picture, what the swampland might look like. So there are a variety of successively stronger no-go results, which we won't discuss today, that make an explanation of dark energy in classical string theory very difficult. So we'll therefore need to understand something about quantum string theory if we want to explain dark energy or quantum gravity in de Sitter space, should any such backgrounds actually exist. This is my primary motivation. I want to get to an accelerating universe of some sort and actually have a definition of quantum gravity in that universe. What do I mean by non-classical string theory or quantum string theory? All I mean by this is a background in which the space-time curvature, or equivalently the space-time cosmological constant, changes because of string quantum effects. So this is something we just generically expect to be true for non-supersymmetric vacua. There's no reason why loop effects or string non-perturbative effects shouldn't modify the cosmological constant. And it's worth distinguishing between two classes of non-supersymmetric vacua. Vacua that are solutions to tree-level string theory, i.e. vacua that have a conventional Walshy conformal field theory description from which one can begin to compute loop effects. And what we might call intrinsically quantum solutions, which don't exist unless you already include string loop or string non-perturbative effects. The latter case appears in a lot of the landscape constructions. So there have been very interesting studies of what we might call these intrinsically quantum backgrounds, which have typically been studied in the form of ADS cross a sphere by many authors listed here, incomplete list certainly. And to get an idea about how this works, we can just look at the dilaton equation for, say, the NS sector of string theory. And if we want solutions that, say, have constant dilaton, then there's a condition that you could balance the flux, which is a classical term here. By the way, does this cursor show up on the screen at all, or is invisible? Can anyone hear me? No? Oops. Sorry. Okay, good. So you could imagine turning on some flux classically at tree level and balancing against some loop generated potential here denoted by e to the alpha phi, and get a constant solution for which this Laplacian term would vanish. And these the solutions that were studied of the form ADS cross sphere are exactly of this type, and they can even be made weakly coupled by increasing the amount of flux through the sphere, say, or through spacetime if it were electric. But these solutions only exist because of the potential term. And if you were to turn it off, there would be no tree level solution. It's a very interesting question to try to understand how to do perturbation theory around such a background, which should in principle be possible. There are also very interesting swampland conjectures roughly suggesting that stable non-supersymmetric ADS spacetimes do not exist. And there is no ADS CFT holography unless there's some supersymmetry in the story. And these conjectures were put forward by Uguri and Waffer and Frey-Vogel and Kleben. On the other hand, there are some explicit field theory constructions that at least suggest that suitable non-supersymmetric CFTs might exist. I think the most prominent one is by Giambi and Perlmutter. And that argument shows basically that at infinite n such a CFT exists, but not that at finite n it necessarily exists. So there's something to be understood. These constructions typically involve starting with a supersymmetric theory in the ultraviolet and perturbing it by some double trace operator, and then trying to understand the resulting infrared theory to see whether or not it's a CFT. But the question is still, I would say, unsettled at the moment for finite n. All right, today I want to revisit one of the most basic ingredients in all these landscape discussions, which is to what extent should we draw a picture like this picture of the effective potential? Something that looks like this, that we might draw in classical mechanics, and you can imagine a ball rolling around from vacuum to vacuum. And we're going to try to explore this question in the context of the O16 cross O16 heterotic string. Okay. So I'm going to come to the second part then, which is the heterotic potential energy. So there are three known non-supersymmetric strings in 10 dimensions, about which I think we've heard repeated discussions in the workshop so far. The oldest one is the O16 cross O16 heterotic string. There's a type 0 prime B string discovered by Sagnotti, and the SB32 open string theory described by Sugimoto. Because supersymmetry is broken in each of these strings at string scale, there'll generically be a one loop potential for the dilaton. And indeed, for each of these strings in 10 dimensions, that one loop potential is positive. It has the same sign with different powers of alpha, depending on the string. For example, the O16 cross O16 heterotic string can be constructed as a orbifold, a Z2 orbifold of either of the superstrings. And in that particular case, the one loop potential is some number which is finite and computable, and one loop times this power e to the 5 halves phi in 10 dimensions. Okay, Today, I want to talk about toroidal compactifications of this particular string, of this O16 cross O16 string. And a tree-level solution corresponds to a flat torus, I'd say a d-dimensional torus, with a flat gauge bundle. And we're going to assume that gauge bundle can be deformed to the trivial connection. So not some non-trivial components of the moduli space, which can certainly exist as you go down in dimension. And in this old story, the moduli space of such compactifications was described by Narayan, and the Narayan moduli space takes this form. In fact, I'm going to go even simpler. Instead of looking at tori of higher dimension, we're just going to look at a circle. This case was studied more than 37 years ago by Ginsburg and Waffer, but it was a kind of critical ingredient in the later discussion. So I want to go back and revisit it here. If we only consider, say, the radius of the circle, then there's one special distinguished point in the moduli space, which is the self-dual radius of the T-duality, where R is root alpha prime. And in heterotic string, at this special point, the gauge symmetry is enhanced from SO16 cross SO16 to SO16 cross SO16 cross SU2. I'm going to be very sloppy about the global structure of gauge groups, because it's not really going to matter for most of our discussion today. So O16, SO16, I'm not going to worry so much about global factors. The moduli space, however, is not just the radius of the circle. We can also turn on 16 Wilson lines on the circle. So it's a 17-dimensional space. And as you tune the Wilson line moduli and the radius simultaneously, there are other special points where the gauge symmetry can be enhanced. So it's not hard to argue that each of these critical points where you get enhanced gauge symmetry is an extremum of the one-loop potential. So that's a place where you might expect your compactification to settle if you let it, if you just let it evolve. And we found a list of all the points of maximal enhancement. And what we mean by maximal enhancement is a rank 17 gauge group without any abelian factors other than the graviphoton. The graviphoton never gets enhanced in this story. It just sits there as a U1 that's just floating around. So we don't worry about the graviphoton, but we worry about all of the gauge bundle coming from the left movers. There are 107 such points on the circle, though most of them have tachyons. If we restrict our attention to the points without tachyons, there are 8 maximal enhancement points. So they're listed here. They can be encoded nicely in a Dinkin diagram, whose details I won't go into right now, or I think we'll run out of time. But you can see the algebras for the different groups. So this case is SO16 cross SO16 cross SU2. This is SO16 cross SO18, and so on. There are this collection of 8 maximal enhancement points. Any one of them you might think could be a reasonable place on which to build a stabilized string solution. Now, the talk has a title, Saddles, because we found something that was kind of surprising. Every one of these critical points turns out to be a saddle point of the potential. Not one of them is actually a minimum. And this is kind of strange. At least I didn't expect it. And this is different from what people had thought in the past. So I'm borrowing a slide here from my collaborator, Bernardo, where we can label what this potential landscape looks like. So of these 8 extrema, only one of them has a negative cosmological constant. And it's a very weird point in the moduli space. If you sit at this point and you move infinitesimally in any direction, turning on any of the other scalars around that point, you immediately encounter a tachyon. We'll come back to this in a moment. So it's a point that's completely surrounded by tachyons. It itself has no tachyons, but an infinitesimal motion away from that point lands you at a point with a tachyon, and the potential drops to minus infinity. The potential is a very weird object here, not a function in any usual sense. The remaining points all have positive cosmological constant. There's the first one we discussed, SO16 squared cross SU2. This was believed to be a minimum in the past, but here we've seen that it's actually not a minimum, but a saddle. There are some directions in which the cosmological constant will go down. And then there's a collection of other points here. Some of these are at the boundary of a region that becomes tachyonic. It's a very rich potential landscape. The one extremum with negative cosmological constant is very strange, and it highlights the extremely rich and peculiar nature of the potential energy as computed in this most straightforward way. Ginsburg and Barfoot called this kind of phenomena a knife edge, in analogy with the knife edge seen on Capitol Peak, which is a 14,000-foot mountain near Aspen that one can go and try and climb. And people try and cross this knife edge, but you fall off to minus infinity on either side, and that's basically the end. You fall off that mountain. On the other hand, some people will apparently find it a nice place to get married if you're comfortable enough walking along a very tight knife edge. So here's another look at this potential landscape. It's too large to depict. There's too many parameters to depict. So we'll just turn on one Wilson line modulus, A, and set the others to 0, and then tune the radius. Here, hiding in the corner is, or here manifestly is the point SO16 cross SO16 cross SU2. And the directions which become more red are directions in which the cosmological constant decreases. So you can see that in some directions it's increasing, but there are some directions here where it will decrease. That same point, that same enhanced symmetry point shows up here. And this is the point SO16 cross SO18. Now, we believe the lines of enhanced symmetry that connect these points are actually geodesics in this moduli space. And we have some argument to that effect at the moment. Well, what are we to make of such a bizarre and rich potential landscape? I mean, is it physical to have a point like a knife edge, where if you move infinitesimally away from that point, the potential energy drops to minus infinity? It seems very unphysical. So we might wonder, could all this be coming about because we're starting with something that's not actually a solution of string theory? We're starting with R9 cross a circle, which is a tree-level solution, but a solution that doesn't stabilize the dilaton. We'll come back to this in a moment. Just in this context, one might ask, can you build domain walls that interpolate from along geodesics in field space from one extremum to another, say from here to here? What would such a domain wall look like? And a very natural question is, if you go beyond S1 to higher dimensional tori, are there actually minima of any sort, or is every extremum going to be a saddle? There are many more fascinating questions about off-shell quantum gravity along these lines, but I won't follow them right now. Today, I want to show that we can actually still use this to build stabilized solutions in the O16 cross O16 string. And the examples are going to be of the form of ADS3 with no supersymmetry, but with all moduli stabilized, but with now the worry about these extra saddles. Okay, let me explain the embedding in the last few minutes of the talk. Again, perhaps part of the reason for the peculiar nature of the potential energy is that we're computing the potential around the tree-level solution, which itself is unstable at one loop. There will be a dilaton tadpole generated. So the question we might naturally ask is, can we stabilize the dilaton at weak coupling and then compute the effective potential? As a first approach to this problem, I wanted to actually construct what we might call non-supersymmetric string islands. These will be compactifications that have no CFT moduli, which would leave only the dilaton as a modulus to worry about. And then to convert the one loop potential that would stabilize everything here to a vacuum energy, we'll want to stabilize the dilaton. And let me sketch how to do this. So it's useful to work in 3 dimensions where we have a lot of control, and we have the ability to turn on an electric H-flux through spacetime without breaking Lorentz invariance. There's a well-studied Freund-Rubin solution in the context of the type 2 string and the heterotic string, the supersymmetric heterotic string, of the form ADS3 crosses 3-sphere crosses 4 torus. And this background only has NS flux, so it has a good worldsheet description. It has an ADS length scale L, which is set in terms of the string scale by the amount of flux going through the sphere, N5. The amount of flux going through space-time, the amount of electric flux, determines the dilaton, which is also frozen. And that's the key point. This background is a background in which the dilaton is not a free parameter. It's actually determined by flux quantum numbers, by this ratio. So we can tune it to be arbitrarily small. Now, this has a lot of moduli still. This 4 torus can be any shape and size. So if we could replace that 4 torus by an island that breaks supersymmetry, we would generate a one-loop potential independent of the ADS cosmological constant. The natural way to try to do this is to look for some asymmetric quotient of T4 that would kill all the moduli. Such a quotient was found by Dabokar and Harvey in the past, but it preserved a lot of supersymmetry, actually half the supersymmetry, roughly the same as a K3, but it had no moduli. We've actually tried to find an island of this type that breaks all the supersymmetry and have yet to succeed. Either you generate tachyons or you regenerate gravitinos and supersymmetry from twistor sectors, but it's not ruled out yet. But note, the key thing for us here is that the dilaton is already massive at tree level, and the string coupling can be made weak. So instead of looking for islands, let's evade this problem and replace our 4 torus by another sphere, another SU2WZW, plus a circle. This only has NS fields turned on. There's now an extra parameter N5 hat, parameterizing the flux through the new 3 sphere. And it's again been well studied in the supersymmetric context. It has one irritating feature, which is there is a tachyon exactly at the BF bound. It's not below the BF bound, but it's exactly at threshold in this background. So if we're going to perturb this background by a one-loop correction, we have to be careful to make sure that tachyon doesn't go below the BF bound, but actually stays above it. Still, there's a circle there, and the circle, along with the dilaton and Wilson line moduli, might destabilize the background. We'll try to cure these problems. This background is NS purely, so it has a nice wall sheet description. Let's just study it from a space-time perspective. So Einstein-Hilbert plus dilaton plus flux. We take a metric of the form sphere, cross circle, and we KK reduce to find some effective potential for the sphere, radii, and for the dilaton. When you do this and minimize, you find, as you would expect, the size of the spheres, L and L hat, are set respectively by the flux quantum numbers, N5 and N5 hat. And the dilaton is also fixed in terms of a ratio, which is morally, again, of the form N5 to some power over N1 to some power. Again, a ratio of N5 to N1. So cranking up N1 leaves the ADS length scale listed here fixed, but can make the dilaton arbitrarily small. So it has all the features of the ADS3 cross S3 cross T, for example, with some added complication of an extra flux quantum number. Okay, just to show you, I'm not kidding you. I just drew the potential here, the tree level potential for some choice of flux values, and you can see there's a nice minimum. It's supersymmetric in the superstring, so that you can't have a BF violating tachyon, but again, there is one exactly at threshold, which complicates our life. If it had not been exactly at threshold, this analysis would have been much easier. Now we can use the one-loop potential we were discussing for the heterotic string on R9 cross S1 to deal with the S1 moduli. So we initially had followed Ginsburg and Vafa and thought that the self-dual point, which is sort of the most natural distinguished point in that moduli space, was actually a minimum of the potential. If it had been a minimum of the potential, it would have masked up the radius of the circle, and it also would have masked up all the Wilson line moduli. Everything would have been masked up. And we could have just forgotten all of the massless modes that came from the tree level string. But now we know it's not quite true. There's actually a direction in which the cosmological constant decreases, so there's actually a tachyon at that extremum. And we have to worry about it a little bit. If we ignore this issue for the moment, I'm just going to sketch what happens when you include the one-loop potential in a couple of pictures. The cosmological constant gets shifted up by the potential, but it never gets shifted up far enough to become positive. It will always be negative, but it will move depending on the size of G string, which is correlated with N1 here. Similarly, the spheres themselves, whose asymptotic size at tree level is to the far right, become a little bit smaller as you include the one-loop correction. And lastly, the string coupling itself, well, this is the most interesting part. The string coupling itself approaches the tree level value for very large N1. And as it gets smaller, the tree level value would have diverged as N1 goes to 0. But because of the potential, it cuts off and approaches a finite value as N1 goes to 0. So in this regime, for a very small N1 or N1 going to 0, you'll hopefully find one of these intrinsically quantum solutions mentioned earlier, which wouldn't exist without the one-loop effect. Here's actually a direct comparison. GS0 in red is the one-loop corrected string coupling versus the classical string coupling, which just diverges for some fixed values of the fluxes through the spheres. It's very neat that the thing gets bounded. Really, these non-supersymmetric strings seem to abhor at one-loop strong coupling. They just don't let you go into a strong coupling regime. Okay, just to check that the string coupling can be made weak everywhere, if we just set these fluxes through the spheres to be the same value n, and you set n1 to 0, you'll find that the spheres scale with n, and the string coupling scales with 1 over n still, regardless of the fact that there is no electric flux at all, classically now, to stabilize the dilaton. So you really can maintain weak coupling, it looks like, even without electric flux. Okay, so what changes because of the saddle? So everything I told you, I initially would have told you a few months ago on the assumption that that self-dual radius was actually a minimum, but it's no longer a minimum. Now it's actually a saddle point. And that means there are tachyons that come out from that extremum, and we have to worry about them again. But the mass of those tachyons is all suppressed by G string. So for sufficiently large N1, hence small string coupling, all of those tachyons can be pushed above the BF bound. So what seems to be happening, at least this is our current take on it, or my current take on it anyway, is that we seem to have a phase structure induced in N1, where perturbative stability can be lost as you make N1 too small in a way that depends on the ADS length scale. And we're trying to make this more precise to see what this phase diagram would look like. Okay, the knife edge feature is very strange for the potential computed on R9 cross S1. And I think it just reflects a peculiarity of trying to define an off-shell potential in string theory. That potential looks discontinuous as a function of moduli and even unphysical. But it might be the case that if you started with ADS3 cross S3 cross S1, which is a solution that's stabilized, and compute the potential, there might be an open set around each of these extrema in which the potential is smooth. That's something we're trying to check currently. And that would give a way to access, for example, that one special extremum that was completely surrounded by knife edge, the one that has a negative cosmological constant. Let me summarize. Since my time is up. It looks like we still have a completely non-supersymmetric ADS solution that's perturbatively stable. It's almost certainly non-perturbatively unstable. It does have a worldsheet description, so you can study it, and you can compute correlation functions in the worldsheet that should correspond to holographic correlators in whatever the dual holographic theory is. Maybe not a C of T precisely, but whatever it should be. It has a string coupling that can be made weak, and it has an intrinsically quantum limit, which I should now modify and say could be perturbatively unstable, depending on the value of N5. That's something we still need to understand better. So modulo this new issue of tachyons from the S1 saddle, it still appears to be free of tachyons below the BF bound for certain ranges of flux quantum numbers. And that's the bulk of the story. And hopefully, again, the worldsheet correlators will teach us something about holography. I should end here. Thank you for your patience.
Thank you. Questions?
Savdeep, this is Augusto Sagnotti. Hi.
Hi.
I have one question because I got lost at some point in the discussion. When you went to estimate this upper bound on the coupling constant and the like, the tachyonic nature of certain directions was not taken into account, or was it? You go back a few slides, I mean, to...
Yeah.
For instance,
Like
when you have this thing, for instance. Are you assuming that the saddle is not there, or what happens to the saddle in this picture?
No, you're completely right. In this, I lifted this from a prior talk where the saddle was not taken into account, and now, indeed, it could simply be the case that you end up unstable at some point here, say, before you can reach the point where you turn off the electric flux. So the values of so we're still computing the masses of the tachyons from the S1 saddle now, but they're suppressed by basically N1. So they get bigger as N1 gets smaller. And indeed, actually, yeah.
But you see, there is also another possibility, because once the coupling starts to grow, in principle, there could be higher order effects that continue to play your game. I mean, in other words, the balancing was successful insofar as GS was receiving an upper bound. If you go up, then you cannot exclude that things get settled with, a resummation of higher order terms. I mean,
yeah. So you say higher loop corrections could become important.
Exactly, it could become important. It could do the job for you. I mean, somehow it's not. So in a sense, it's not lost yet. I mean, with the tadpole.
Yeah, the phase structure of this story is much richer than I would have guessed. I mean, it looks like there is a good perturbative story here, up here, and then something weird is happening as you get down here. I think if this weak gravity conjecture is true, then you should decay non-perturbatively down here anyway. So whatever's happening here, one has to worry about eventually. Maybe not perturbatively, but certainly beyond perturbation theory. Indeed, yeah, that's a good point.
Okay.
Hi, I have a question about your the saddles. So you said at some point that all the extreme are saddles, but then you also have the isolated minima, or also the isolated minima are kind of unstable?
Well, the isolated minima is unstable in an even weirder way, because where is it? Well, it's denoted on its own here with its own picture, because if you move infinitesimally away from it in any direction, and this is a very weird phenomenon. I don't know how to explain it because I don't understand it properly. But if you move infinitesimally away in any direction, you generate a tachyon instantly. So if it's literally balancing on the edge of a
it's a maximum of some sort of a maximum of the potential. So if you include the full back reaction, I guess it will become a smooth maximum of the potential, right?
Yeah, though being a smooth maximum is not lethal for ADS, right? You can be an extreme as long as the slope is gentle enough. So it's still okay to be a maximum even, as long as the mass of the tachyons is not too extreme.
Yes.
But I think just in general, I'm just wondering if you take the back reaction into account, is there even an open set around this where you would say the potential is a function even that you can sort of make sense out of?
Last question, Emilian.
Hi. Question, did I understand correctly that you are considering asymmetric orbifolds of SO16 times OC16 heterotic, and in some example you found gravitinos in the twisted sector?
Oh, sorry. Good. Yeah, I apologize. This talk is a little bit more mangled than it should have been. The asymmetric quotients we were looking at were in the superstring. So we were actually trying to do that initially in the superstring to break supersymmetry in the superstring completely. And then the jump to, and there in the superstring, quotients of T4, every quotient we tried of T4 so far, either preserved supersymmetry or generated tachyons. And we couldn't find one that had no moduli and broke supersymmetry without tachyons in the story. At that point, we switched to the O16 cross O16 string, where we do no asymmetric quotienting of any kind. It's just the circle cross sphere, cross ADS.
Okay, thank you.
Okay, so let's thank Savdeep again. The last speaker this session of today is Ralph BLUMENHAGEN.
So I have it in the right direction. Very good. So first of all, I would like to thank the organizers, in particular Augusto, to invite me here to Pisa. It's my first time here, and it's really a pleasure to be here. So today, this is the final talk today. I would like to talk about dynamical cobordism and the end of the world. And so this is work that in various collaborations together with Niccolò Cribiuri, Christian Kneissl, Andriana Macredou, and Chuying Wang, all from Munich now. Okay, so it was already mentioned in some of the talks that we have the most basic swampland conjecture maybe is, and I think there is almost no doubt about it that this is true, is the one that says that there are no global symmetries in quantum gravity. So I don't repeat them here, but there are quasi-classical arguments based on black hole evaporation. And in string theory, we know that if we have a global symmetry, say on the two-dimensional worldsheet, it already leads to a gauge theory from the space-time perspective. So in some sense, there is not much room for global symmetries, yeah, from the space-time point of view. And if one seems to detect one, it actually, there are two ways. This is physical intuition. How to get rid of them, it needs to be gauged or broken. So if you gauge it, you introduce a gauge. Where's the pointer? You introduce, sorry for that. Yeah, if you gauge it, so you introduce a gauge field, and then you have some equations of motion, that's showing here, or Bianchi identity. Or if you break it, so what you do is that the current is not preserved, so you get a 1 degree higher form on the right-hand side, which will be important in a moment, so please keep that in mind. Okay, so this conjecture, so to say, gave rise to an interesting observation by McNamara and Waffa. They pointed out that if you have, so to say, a new object, a non-vanishing cobordism group with respect to some structure psi shown here, this will give rise to such a global symmetry. More concretely, if you have a cobordism group level n, omega n, it will give rise to a d minus n minus 1 form global symmetry. So this should be preserved. But this we don't want to have, as we said, so we should actually nullify it. And so the idea here is now, okay, so we started, roughly speaking, at the wrong place. So we were choosing a structure psi such that is non-vanishing. So you need to refine that structure, adding more stuff, such that eventually the cobordism group vanishes. And the unknown thing is, so what is the full cobordism group structure of quantum gravity that eventually nullifies all cobordism groups? So this is quite abstract. So there's now a body of literature into this, and I will tell you in a moment why or how to make it a bit more concrete. So maybe just to be on the same page, it was already mentioned in one of the talks by Ivano yesterday. So what is a cobordism group? So this is about classifying manifolds, equivalence classes of manifolds of, say, d dimensions. So m and n, you should think of n-dimensional manifolds. And then you introduce a higher dimensional, one dimension higher manifold W, such that the boundary of W is the disjoint union of these two manifolds. Then you are saying that m and n are cobordant. And the point is that this W, I mean, it can have arbitrary topology as long as it preserves the same structure. Okay, so the same structure as m and n. So from the lower dimensional point of view, so we think of these cobordisms to describe compact spaces, okay? So from the low energy perspective, so to say, from the flat space-time point of view, such a cobordism W, you can think of this as a domain wall separating the two backgrounds M and N. And then the cobordism conjecture, so this is just more or less a citation from this paper by McNamara Waffa, says that topologically all quantum gravity allowed configurations are connected to nothing via finite energy domain walls. Okay, so this is the idea, still very abstract. So, but maybe make it a bit more concrete to look what it means in string theory, where we have many examples of that. But so far we didn't talk about cobordisms in that context. So if you do the gauging, and this is now essentially the contents of these two papers here that appeared last year and the year before. So we know in string theory many symmetries are gauged. So we have generalized Bianchi identities of the following form. So on the right-hand side, usually we have various objects. We have D-branes that couple to this, say, Ramond-Ramond field. And in addition, we have other contributions, which often come from the Wess-Zumino or from the Chern-Simons term of the D-brane action. And these are usually expressed in terms of topological invariance. And this is already what this means. So you can think of cobordisms. So these topological invariants, these geometric ones, these are sort of the generators of the cobordism groups, okay? And the localized branes, we know that they are classified by K-theory. So in this gauging, for instance, you are having added already a combination of cobordism invariants, of cobordism invariants and K-theory groups, yeah? So they talk to the same, they are gauged, so to say, by the introduction of the same gauge field. So one way of thinking or physically about these cobordism groups is very similar to think of them as K-theory groups classifying D-branes. Yeah? And so the geometric contributions are classified by cobordism. And indeed, there is a deep mathematical theorem relating certain K-theory groups to cobordisms. There's even an isomorphism between the two. So the unitary ones are related to the spin C cobordisms, and the orthogonal ones, which classify D-branes in type 1 string theory, are related to the spin cobordism groups. I think that, well, this would be interesting for the Sugimoto model, indeed. Yeah, I'm not sure. I mean, I think the cobordism groups have been partially computed for symplectics. I think in your paper you did that. But I'm not sure about the results. So in most of the literature, you just find these. But I think it's known. So one way of thinking of the global charges, so to say, classified by K-theory and cobordisms is just if you now turn off the gauge field, so if you haven't gauged it, ungauge it, then you see that each term comes with its own global charge, and this gauging combines all the ones. So the cobordism groups, in some sense, are nothing else than these geometric contributions that we are all familiar with. But this talk is not about so much gauging. This was just a slight review of these two papers. So here is more about breaking of symmetry.
Ralph?
Yeah.
Can I ask you one question?
Yeah.
Could it be that this relation that you wrote naively seems to relate branes and orientifolds?
Orientifolds would be another contribution, I think. So, yes, indeed. So there can be more. There can be more. So in this sense, so to say, these are smeared out geometries.
No, I'm saying very naively. K-theory has to do with the classification of branes.
Yeah, so there should be a new.
And the cobordism group, I mean, should have
the geometric ones and the orientifold planes. I think I have not really classified in that sense. I mean, you're just changing the structure, so going from spin C manifolds to spin manifolds. By this, you include already the O9 plane in this game. Do you have a question or? Yeah, you want another comment? Yeah.
The planes can be classified by the oriented boardism, right, rather than the spin boardism. And there is an inclusion, like you can, there's a Whitehead tower of boardism groups, so you can essentially think of introducing both branes and O-planes together by putting together the classes from oriented and spin boardism. That's one way to do it.
But one should be sure, so this is only counting or classifying house numbers in some sense. So these are just numbers, what are the charges and what are the values of the charges. So it's a very rough topological tool, so to say, we have. No? So it's not very detailed, but it's off-shell. That's one of the main points. So it's not relying on explicit solutions of string theory. It's not an on-shell concept. Okay, so let me come to breaking of the symmetry. So as I've shown you, so we introduce a higher dimensional form on the right-hand side. So this you can think of as the Poincaré dual of a lower dimensional object of codimension 1 actually in the non-compact directions. So you can think of this as a defect. This is what this picture there suggests. So what you do now here geometrically is, so you have your manifold, which before M, which was before, was not cobordant to 0. But if you add this defect, so to end up, so to end at the end of this cap, so to say, then the combination of M and the defect, this will trivialize these two things, and then it's cobordant to 0. Of course, this is hard to compute because so far we don't know really how to compute cobordism groups with such singular objects instead, but this is just the idea, the picture you should have in mind. So that configurations, or if you have a non-vanishing cobordism group, that tells you there are two ways. Either you gauge it, okay, if it's not possible to gauge it or it's just not gauged, then you need to introduce defects or try to introduce defects in order to trivialize it, to cap off this manifold in this way. And this is very reminiscent, now I'm coming to the actual talk that I'm giving today, to, this was realized by the Spanish group around Anglo Ranga, that it is conceptually and from the idea, this is very similar to some problems or to potential solutions to problems we had with precisely these string constructions we were all talking about already in a couple of talks here that have these running dilatons. Yeah? So these exponential potentials, so they have tadpoles. So now, but there's a conceptual change now. Before everything was topological and off-shell, but now we are literally talking about dynamical objects, and we are talking about solutions. We have a metric, and we have fields, and we are looking at equations of motion. So there is a conceptual shift, but I think the logic behind that is very similar, or at least the cobordism conjecture, so to say, gives a new perspective on some of the puzzles we had with these solutions. Yeah? So I think this I don't really have to say again. So there are non-supersymmetric tachyon-free constructions, we've mentioned in the previous talk. They have brane supersymmetry breaking, and we have the Sugimoto model, and so on. So this will be of interest next. This is very, so here it is. So if we have this dilaton tadpole, so we can try to implement it or take it into account in our effective action by such a term, as has been done by DUDAS Murat, I think, for the first time. And for the Sugimoto model, in 10 dimensions, you would just add something like a potential term, depending on the dilaton phi in this way. But here now we consider a much more general framework, where we leave the dimension, the non-compact dimensions, free, and as well as the parameter in the potential. So B for the Sugimoto model is 3/2, and capital D is 10. There's also the T-dual Sugimoto model by Anna Maria and myself, which if I have time, I will say a few words at the end. But the main topic here will be now on a much simpler case, just to make the case, to explain what the idea is with the model of DUDAS and Murat. So what these people have figured out, or what they propose, is, so we know that if you take this back reaction now into account, so you solve these equations of motion, then we find sort of, we cannot preserve the full symmetry of the model. So the simplest case is when we compactify, or we have a spontaneous compactification of one additional direction on which the dilaton then non-trivial depends. And it turns out that there are solutions where this distance is actually finite. And if you now, and moreover, there will be a singularity at the end of this finite interval. So delta is the distance to this singularity, and D is just a canonical calligraphic D is just a canonical normalized field phi. So there is a universal scaling behavior. Now, so D goes to infinity or plus or minus infinity at this end of the worlds, and then there's a certain scaling of the proper distance delta and of the curvature if you approach these singularities in this way. And delta needs to be fixed, but you always find this nice behavior. And so to say, objects that have this behavior, so they are called, so to say, the end of the world branes. Yeah? But this is just, you find solution and you look at the singularities and then try to detect what kind of behavior I expect when I approach this singularity, but it doesn't resolve the problem of how to cure the singularity, to close it off by what kind of object. So the question is actually, is there really here, in this case, a codimension 1 brane, a defect, like in our former picture, that can close off such a singular solution, and what are its properties? Okay, so these objects, these true objects are called end of the world branes. Okay, so here now I follow, and there were of course previous work, which I'm also citing in the course, but here I'm just following out the notation and what we did in the systematic analysis in this paper with 2 students from Munich, Kneissl and Wang. Okay, so this is our old friend. So we are now looking for solutions. So we are generalizing the DUDAS-Murat solution. So we make the usual ansatz that preserves not maximal Poincare symmetry, that's not possible, but to preserve d-1 dimensional Poincare symmetry and have a non-trivial dilaton profile along the direction y. Okay, so then we construct solutions for arbitrary parameter b. We apply the usual tricks that have been found by Dudas and Murat, so that you could redefine. First, you make this ansatz b equal to proportional to phi. This simplifies your equation. Then you can solve one of them explicitly by writing it as a cosine of another function and the sine of another function. And then you get the remaining, the third equation of motion then takes the following form, where I now have also introduced the parameter b critical here. And you find that this is a thing that comes out, and it has the value that is shown below. So it's given in terms of the number of dimensions t in this, by this following quotient, a quotient that often appears, by the way, in all these swampland discussions. Epsilon 1 and epsilon 2 are just sign factors that you are allowing to solve this quadratic equation. Okay. Okay, so there seems to be some critical behavior. There's a critical value that we are seeing here, and also in this paper by Ivano and friends. That's really a nuisance here. Okay. Here we are. And we are looking at solutions of finite size in the y direction. And we want to extract, or to check whether we always have this scaling behavior that we expect for end of the world branes. And indeed, this will be true. And we have to make sure that we are, so we'll see that the type of the solution, so there will be trigonometric solutions or more hyperbolic solutions. This depends on the value of b relative to this critical value. So whether you have b larger or smaller than the critical value. So note that the Sugimoto model, as I mentioned, is just on the critical value. For this, we can also find a solution. And the other case that was also mentioned today, massive type 2a, so when you turn on a non-trivial Romance mass, this leads to the value, or it's described by the value b 5/2, which is larger than the critical value in 10 dimensions. This becomes important in a moment. Okay, so now we look at the solutions. I mean, this is a boring thing, but we ended up with the following table. So what is this? So maybe I just explain the first region. So forget about the sign factors. These are maybe details. So if we are in the region that b is larger than b critical, we find the following end of the world behaviors that we wrote here in terms of ETV branes. So L means left on the left-hand side, right on the right-hand side, R on the right-hand side. The minus means that the dilaton goes to minus infinity, so which is the perturbative regime. Plus means to plus infinity. So if you're concerned, of course, here we are actually losing control over our effective action. This is what we expect. But we just treat this case as well because it just shows the same behavior or analogous behavior. And that the delta coefficient, that's the most important thing, is either b, as you can see, or b critical. On some, at some singularities we get the delta with b critical, and if you are in this middle region, where b is smaller than b critical, all the branes always have delta equal b critical. So you never find a delta that is below b critical up to this factor squared of 2, which is just a normalization thing. So this is interesting. Yeah. So delta seems to be bounded from below. Oh my God, come on. Okay, so now the question is, can we introduce an object that close to its core has precisely the same behavior as these end-of-the-world branes that we expect to exist, okay, and which close off space-time. So they should have boundary condition that describe end of the world. First of all, it's a codimension 1 brane, so there is now this delta function. Now we are second step now. Okay, we're looking now for explicit solutions. Then we require, for instance, for a left brane that, so it ends up at the space to the left. So on the left of it, there should be nothing. So the GS should be 0, the matrix should be 0. And to the right, well, we would like to have a non-trivial solution to the bulk equations. And then the corresponding jump conditions coming from the delta function. So if you go into the equations of motion, if you manage to change the slide and go into the equations of motion, you find immediately, if you just look at the equations of motion, that consistency of them requires you that this parameter in the exponential here of the end of the world brane is fixed and precisely essentially to the critical value that we found before. Yeah? And implementing the boundary condition, the tension comes out negative. And close to the core, of course, here we have slightly different coordinates. Yeah? But if you move to express everything in terms of the proper distance from the brane, you find precisely the same behavior for the metric and the dilaton as we found close to the end of the world brane in the previous DUDAS-Morat solution. Yeah? So this is a candidate, or this is clear that this brane can close off the former singular solution because it just has the same behavior close to its core. Yeah? In other words, you can take the DUDAS-Morat and implement in addition the boundary conditions from that brane. That's another way of saying it. There should be no obstacle. Okay, so just to see what that is. So if you now go to 10 dimensions, just choose 10 dimensions and do the computation or change the brane action to string frame, you find the following action. So these branes, these new branes have tension e to the that scale like e to the minus 3 phi or e to the minus 3 over 2 phi. So these are not standard kind of branes. No? So they are not neither D branes nor something else, or not NS branes. So these are supposed to be new objects. So the summary up to now, how am I doing with time? 10 minutes? I think I have 10 minutes, no? 5. Ah, you rush me. Okay. Usually if I'm rushed, I went slow. No, I'm not rushed. Okay, so I have only 4 pages. I'm almost done. Okay. So if you now look at our table, so we identified now the end of the world brane. These were neutral objects, okay? Just have also a dilaton field, had tension. And we found all the black ETV branes here we now, so to say, constructed explicitly. So what remains is the one where we have the blue ones where the delta coefficient was proportional to B, and B was essentially arbitrary as long as it's larger than B critical, okay? So something is missing here. So we're not getting everything. So what is missing? To get an idea, you can look at the Romance mass case, massive type 2A. So here we had a case where B was larger than B critical, namely 5 over 2. And this, we don't know how it was realized. So there was a zero form flux. So we expect now that maybe so there's a flux in the game, so that at the end of the world, something should compensate that flux or should be charged under the same Ramond-Ramond field, of which this is the flux. So this gives you rise to the idea that maybe we should also look at charged end of the world branes. So again, we write down the most general up to quadratic order, of course, action for a charged object now. Again, codimension 1, so the delta. So the second line is the D-brane action, is the brane action with a priori arbitrary coefficients BC and AC. These are completely new objects now, new coefficients that we need to fix. And then also the magnetic coupling to the 10 form, to the 9 form to the 9 form potential C. Okay, so this is a bit more complicated, of course. So the equations of motion become longer and everything. So I keep it short. So the solution you can find in the paper. surprisingly, of course, one solution is always known, that is the BPS case. That's not a surprise. We should find it as well. But there are more solutions. So we find the deformation of these BPS solutions, that on the level of the equations of motion. And indeed, this deformation was only possible if BC is larger than B critical. So precisely, essentially, what we are expecting that, remember, we had this constraint, B can never be smaller, and BC will eventually be related to the B coefficient in the Dudas-Morat construction. Actually, it's minus the one here, the second last line. So we're finding the same bound. We're finding the same bound from a completely sort of end of the world brane picture. The BPS case is also included by a certain choice here. And again, close to the core, this solution is precisely the same as the singular behavior of the Dudas-Morat solution. So we think we have a very coherent picture here. Of course, what we don't know is now, maybe Ivano has a better idea now after their work, what is the actual cobordism group that we need to compute for these objects being the defects to trivialize it. So we don't know the structure, but you would expect that there is an omega 0, because we are talking about codimension 1 branes. Yeah, we're talking about codimension 1 defects, that there should be an omega 0 with a certain structure of the Sugimoto model that is non-vanishing. And then the old Dudas-Morat background, so to say, is not taking into account these defects. So it corresponds to this non-trivial cobordism group. So it's not a consistent solution of string theory. It's not allowed. It's not allowed. Only when you introduce the end of the world branes as well, then you have an allowed configuration that is cobordant to nothing. Of course, the important question now is it stable? So this stability is not an issue here. Yeah, doesn't mean anything so far. And also, I mean, they're saying that it's a finite, so to say, you have finite size domain walls between one vacuum and the other, but that's not clear. I mean, I think you can also have situations like that after you trivialize your cobordism group, you just can roll down and your configuration will decay. This we don't know, and we cannot decide from our computation. Okay, 2 minutes. Okay, so we generalized this also to the paper, to the model of Anna Maria and myself. Everything becomes a bit more complicated, and we had a previous paper just on that case. So actually, this end of the world brane were constructed first for this model and not for the Dudas-Morat. And then they were challenged with the question, so to say, whether we can generalize it also to the, in fact, actually more easy case, Dudas-Morat, that this we did in the second paper. But so in the first paper, in this paper that I'm citing here, we were again only considering the 10-dimensional case and the very specific value of this coefficient A. In this new paper, we were also looking at the most general solutions to these equations, and the solution just continues like it was before. So actually in the old paper with Anna Maria, we also were looking at the general configuration line. Okay, so again, there is no maximally symmetric solution. So you can think of this action as being the T-dual of the Sugimoto model, or as the back reaction of a non-BPS D8 brane in type 2A. That's also a possibility. So here we have a bit more structure. So the solution preserves only, we find a solution that preserves only 8D Poincare symmetry, but it has a spontaneous compactification on an S1 times this finite interval. So very interesting. So this already calls for a non-trivial cobordism group omega 1, and for instance with structure spin, which might be relevant here, it's C2. So there is something you need to cancel. And at that time we also found already these log singularities now, point-like singularities on this space S1 cross interval, which were log-like, and we could have no clue what this means actually. So this is why this paper was not really observed. I mean, was just strange maybe for some people because we couldn't make sense of them. But now we have this new perspective. So this would just indicate end of the world 7 branes. And the question then is again, how can we construct end of the world 7 branes explicitly by making even a codimension 2 ansatz now? And indeed, that's the case. This we managed to do. They preserve 8-dimensional Poincare symmetry. They precisely have the log singularities that we saw in the old construction already. And they're non-isotropic now in 2 dimensions. So we make an ansatz which is depending on the angular variable. So it's not radially symmetric. And then we were plotting it, the warp factor, for instance, in an angular plot. So I manage, here it is, conclusions. It looks like this. Of course, we find it independently from the left and from the right brane. But you see, this has a bit of taste of being something end of the world like. So if you long to take the left picture, for instance, if you move into the negative x direction, so there's nothing. There the dilaton is vanishing and the warp factor is also 0. This you cannot really see here, but this is the direction where you cannot move on, you cannot continue. And it looks highly asymmetric. This is just for illustration. Okay, so I end not with two conclusions. So we formulated this into a generalized, if you want, dynamical cobordism conjecture. So if you have a solution for an effective supergravity, I mean not necessarily super, theory featuring a singularity at finest spacetime distance, consistency with quantum gravity requires the existence of an explicit solution for the ETV brane that closes off the spacetime singularity, and the evidence is what I told you, essentially. Okay, thank you.
Questions?
Yes, I wanted to make a comment on the from the gravitational side.
Yeah.
So whenever you, it seems that whenever you have one direction that's singled out, like in Augusto and Gial's solutions with the internal torre, or in Livano's pinch of singularities, there's always the kind of the same asymptotic behavior in some sense. Yeah. So I would expect that in the same way as in the for the 7 and 8 brane, in these cases, something similar should happen for lower dimensions. I don't know if maybe someone should compute. Well, you should compute the right Bordism groups and see. If,
so you want to go to higher codimensions?
Yes, to higher codimensions.
Yeah, I would also. We tried a bit, but it's a bit harder to find the explicit solution, I would say. I mean, in the moment when you give up isometries, you can write many things. Yeah. And of course, at some point, you always make an ansatz with separation of variables and so on. So.
Yes, no, my question is just because maybe with lower dimensional branes, it might be kind of possible to have some worksheet analysis, because that would be the
Yeah. I mean, in particular, if you find an object, I didn't say it. So for Annemarie in my model, so to say, the end of the world brane has tension e to the -2 phi.
Yes.
-2 phi.
Yes.
And this calls for a worldsheet description, because this looks like a defect in closed string theory, no?
Yes.
So,
if you go lower,
like NS5 brane,
if you go lower, I'm expecting, I don't know, something.
Yeah.
More
then you might have a
tensions.
worldsheet description, indeed.
Because, well, for instance, a couple of months ago, there was Tachikawa's paper that did a very different thing with the erotic branes, and there he had a worldsheet description. I think when you have a worldsheet description, there's nothing else that you can say. The brain is there. You're literally seeing the brain.
Of course, this is indirect indication. I understand.
Yes.
Yeah.
I mean, I think there was also a similar old story with the brain between type 2b and type 2a. There, people have a kind of a worldsheet description. There's a paper by Dissler, Fried, maybe was the other author. But here you don't have a worldsheet indication, and that is missing.
In the moment, I don't have a worldsheet description. No.
One comment that may be useful in the future. Many years ago, Perchoff and Riccioni classified brains which have higher powers of
other tension. Yeah.
So it's something we should keep in mind.
Should keep in mind. Yeah, I remember there sometimes these are non-geometric
objects
branes,
which have
like Q branes.
couplings with the higher powers of e to the
I know
-5.
about that. But I think this doesn't. I thought it doesn't fit here. I think they had e to
I
the
think they're in lower dimensions.
-4 phi or something they had.
Yeah,
this I remember.
But it's something to keep in mind.
Yes, absolutely. Completely agree. Very good. Yeah.
Okay. So let's thank again Ralph and all the speakers of today. And I guess we meet at 6:30 in front of the Scuola Normale, and for those who come directly to the bus, within 7, I guess.
So please be on time with Salvatore and Emilian.
Okay, let's start the afternoon session. So the first speaker is Emilian DUDAS from Polytechnic. Will tell us about variations on brane supersymmetry breaking first. Thank you.
So first of all, you hear me? Thank you very much for the nice invitation to the organizers and especially Augusto. It's always a great pleasure and privilege to be back here in this incredible environment, building. So the talk I'm going to talk about, I'll discuss today is an ongoing collaboration with Carlo ANGELANTONJ and Cesar Condescu in Bucharest and Giorgio that you saw already yesterday. And these recent, that's what we're discussing for some time. It's a kind of different realizations of this model with supersymmetry breaking, which we call brane supersymmetry breaking with Ignatius and Augusto, 99. First of all, I'm very impressed about the number of talks on SUSY breaking. This was a very obscure subject long time ago. And here, at least 3/4 of the talk are on the subject. So that's very interesting for me. So since there are two talks, Carlo and me, I'll start with some general discussion about brane SUSY breaking. For some of you, you can sleep. You know which ones, who I'm talking about. For the others, well, no, maybe not everybody knows these things. And then I'll talk about a variation, which is based on some simple new constructions, which are maybe probably well known in the old literature. We didn't find examples. So if you have papers in which similar methods were used in the old days of perturbative oriented constructions, please let us know. But at least the example I'll give you today are new, we believe. So it will be some new realization of brane supersymmetry breaking. I'll restrict myself to 6 dimensions. Carlo will make some comments about 4 dimensions. Some puzzles for us, maybe not for everyone, and some prospects. So let me start, which is a bit inappropriate for a lot of you, but some general comments about oriented constructions. This should have been given by Augusto or Massimo or Gianfranco or Carlo, but just very short comments. So we're talking about oriented constructions. We have closed strings, open strings. This is the cartoon. By the way, all the figures I stole from some lectures of Carlo. Everything you saw, you'll see is Carlo. I should have put it. So there's the standard picture with closed strings, open strings, D-branes and orientifold planes. And the most important part for today, new kind of constructions are the so-called tadpole condition, which is just charge conservation in the internal space, or Gauss law if you want, which tell us that if the flux cannot go to infinity, with the exception of, for example, 10 dimensions, the picture does not work in 10 dimensions. The sum of the charge of D-branes of orientifold should be 0. This is just Gauss law. And when I talk about D-branes and orientifolds, I always talk about so-called background branes, not probe branes that we can always add, like lower dimensional defects. It's an interesting story about these lower dimensional defects also. Carlo will tell you something about it, but I'll not talk about at all about defects. I'll talk only about background branes. And you know the usual story. So if you look at, for example, the cylinder or the other Klein-Bottle Möbius amplitudes, you have this one loop amplitude which have a dual interpretation, loops, and the same diagram can be interpreted as three-level exchange of closed strings coupling to these boundaries here. which can be physical in space-time picture, the branes or orientifold planes. Now, again, very well-known things, but this will appear all the time in my talk. Usually you have the branes and orientifold planes, mutually BPS. There are two kinds of orientifolds. I'm not talking about, there are also some orientifolds which do not exist in perturbative constructions. We don't know how to construct, but I'll always talk about today about the ones which do appear in orientifold constructions. And the difference between, since I see that there are some people more phenomenological oriented, I allow myself to give some simple explanations. So the difference between the branes and orientifolds is that, for example, the orientifolds are like mirrors, so they can have negative tension, for example, which is very unusual. No? Negative tension is very unusual. This would be inconsistent for a dynamical brane, but orientifolds are kind of mirrors, so this is consistent. But there are the standard ones are this negative, what is called a minus, negative charge, negative tension, whereas the exotic ones, which will be the most important for us today, is called O+, which look like a brane, positive tension, positive charge, but they're still non-dynamical. When we break supersymmetry, we have also the anti-particle likes, anti-branes, if you want to call anti-branes, so which have opposite charge. So anti-brane has negative charge like a positron, if you want. The same story for the orientifolds. The object with a bar have the opposite charge corresponding to the orientifolds. Yeah, so in supersymmetric constructions, and this was pioneered by Augusto with the Rome group, with Massimo, with Gianfranco, later on Carlo, the late Yassen, and other people. Davide also, I think. The SUSY constructions contain only mutually BPS objects, for example, branes and this O+ or minus. They can be either only O-, only O+. And again, tadpole condition is just Gauss law. The sum of the charges in internal space should be 0. Tadpole condition requires introducing background branes. For example, we have a certain negative charge coming from O- planes. We have to add an appropriate number of the branes. In my terminology, that is somehow the traditional one of the Rome group, I'll talk about 32 branes, which means rank 16. Rank 16, so usually we call them 16 branes. I'll use this terminology, call them 32 half branes, or okay, this will be the terminology. Now you can also have supersymmetric examples, and again, the Rome group also pioneers this, in which you can have also exotic orientifold planes, but still with a total negative charge, such that you are able to add the branes to cancel the charge and the tension. And you remember that, yeah. So let me start with the simplest example, because this will allow me to present what we constructed in this what we call brane supersymmetry breaking, and why we thought, and we still think there is something interesting there. So the usual example is worked out by Massimo, was out about Massimo and Augusto long time ago, and there was an orbifold, so-called the simplest one, Z2 orbifold, which is 4 parities, if you want, in 4 torus, which is typically product of 2 tori. You can even consider the product of 4 circles, if you want. And this had only standard orientifold planes, O9, which is something which evades 10 dimensions. If you want, it's object which live in 10 dimensions, only negative charge, so you have to add D9 branes to cancel the corresponding charge. And the orbifold generates also localized objects in 6 dimensions called O5 planes. Again, you have to add D5 branes. So you have a gauge group from D9 branes, you have a gauge group for D5 branes. They are U16, the simplest case in which all branes are together, are in the same place, and on the fixed points, otherwise it's different. So the most important thing is the gravity sector, the closed string sector, and the so-called twisted states, localized in 6 dimensions in this case. So the twisted sectors here consist of hypermultiplets in 6 dimensions, which contains, as you see, 4 scalars and fermions. And this is the open string sector. And again, this was rediscovered later on by Gimon Polchinski, and were given a geometric interpretation, which was very useful later on. And the open spectrum is supersymmetric and oscillates, as you see, because of technically because of the Möbius amplitude. So, and this is not the example in 6 dimensions, but I gave you, let's say, the SO32 is 10 dimensions. You see oscillations, antisymmetric, SO32, symmetric, unsymmetric, and so on. It's the standard oscillation. Now, the beginning, again, so I'll allow myself to do a little bit of what was our idea, was to trying to understand some puzzling examples that I think Augusto and his collaborators stumbled upon, which was the following. You're constructing different so-called orientable projections in 6 dimensions. There was a gravitational closed string spectrum, which was supersymmetric. They look to be completely consistent from the point of view, sorry? Ah, okay. Yes. So the closed string spectrum, gravitational sector looked like completely consistent from the point of view of the standard rules, but they could not add open strings in a supersymmetric way. And this was very puzzling. And then when we started to discuss, there was already the time in which people were talking about non-BPS objects. And then we realized that these models contain, instead of standard orientifolds, some of them were completely exotic. So they had positive tension, positive charge. If you have these mirrors which have positive tension, positive charge, and if you want to cancel the charge, you can only do it by adding anti-branes which have opposite charge. So you are forced to start. So you have a exotic orientifold, and you have to add anti-branes. This cancel the charge, the tadpole, but these are mutually non-BPS objects, break supersymmetry, but without having tachyonic instabilities like you have brane anti-brane systems. This was the only idea. Now, from this point of view, this was actually discovered a couple of months before by Sugimoto, so-called Sugimoto model in 10 dimensions. We're not aware of his model. However, the models, from our definitions, what Sugimoto did was we would not call brane supersymmetry breaking. What we would call brane supersymmetry breaking is the following thing. You have a gravitational closed string spectrum which is supersymmetric. You want to add branes. And if you want to add branes, the consistency does not allow you to add supersymmetric breaking. It's just impossible. You have to break supersymmetry. It's not the case in 10 dimensions. Sugimoto model, the same closed string spectrum which has SO32 and USP32 solution. So from this point of view, this was not brane supersymmetry breaking, and yeah. So this was our original perspective. Okay, so you break supersymmetry anti-branes. There is no tachyon instability. The price to pay is that anti-brane and exotic orientifolds have the same sign of the tension, plus, plus, plus. They add up. When you add up, they have a tension, but this tension is not a constant, but it's a runaway potential that you already heard yesterday in the seminars by Ivano, by Salvatore. You'll hear more today, tomorrow. Certainly. So you have what's so-called the Schwarz tadpole is just the tension of these objects. From my perspective, it's so-called untwisted tadpole, if you want. And before going to the current models that we are doing now, the spectrum of the bosons is, in this case, misaligned. You break supersymmetry at this string scale. If you look at the massless level, fermions antisymmetric representation, some gauge group, boson is symmetric. First massive level, it's opposite. They are always, if you want, misaligned. If you want to search the partners of these fermions, you have to go at the first massive level for the bosons, and you can interpret this as supersymmetry breaking at the string scale. It's very similar to Scheck-Schwarz, but the difference between mass level is not the compactification 1/2R, it's the string scale itself. And whereas the Scheck-Schwarz, we understand there are some debates, but in most of people's opinion, it's a spontaneous symmetry of supersymmetry. There is no way here to recover supersymmetry. In the case of Scheck-Schwarz, you send the radius to infinity, you are recover supersymmetry. Here you cannot recover supersymmetry. It's really non-linear realization of supersymmetry. Now, the examples we gave, which was the simplest, and we believed for a long time, for wrong reasons, that's modulo splitting the branes with some lines, is the unique example. This was a mistake. It was the following. So first of all, as I said, this model has exotic orientifold 5 planes. Because of this, we have to add anti-branes. So because of these exotic objects here, you have to add anti-5 branes. But most importantly, in the language of Polchinski understood this, I think, for the first time. In this case, you have in the twisted sectors not hypermultiplets, but tensor multiplets. Physically, as I said, the hypermultiplets contain scalars, let's say in the bosonic sectors. In this case, the tensor contains 2 forms. That's an important difference. As we know from string theory, when you have a scalar, you can see it as this comes from the Ramon sector. It's a 0 form. They come together with four forms also. Tensors, antisymmetric tensor, come together with 6 forms. So these objects now, when you start to put branes in the theory, the branes could couple in a non-trivial way to these tensors. It's not the case for the hypers. So the branes in the original Augusto, Massimo, Gibbon, Polchinski model did not have, in the simplest model, physical couplings to the twisted sectors. Here, we'll have couplings, and the corresponding branes are called fractional. So what will be fractional for mid-brane today would have this localized charge, twisted charge. So this was the gauge group. It's not very important. It is well known that when you put the branes on exotic orientifolds, we have symplectic gauge group. It does play a role in the construction. And I'll not insist here on the spectrum. You have spectrum of this type. You have various bifundamentals. And what is important to note, what is important actually is that we can check explicitly, and actually I should have cited also following up a very nice paper by Gianfranco and Fabio Riccioni, which did the same, what we did with Giad was in 10 dimensions, but Gianfranco did it in 6 dimensions, precisely in these models actually, sorry. You can always identify the Goldstino. As I said, there is a supersymmetry break in the string scale. You don't see the superpartners because it's a string scale. You don't see the superpartners like in Scheck-Schwarz, but you should be able to identify the Goldstino. You should be able to identify the so-called Volkov-Akulov realization supersymmetry, and you can. That's what we did. This is one consistency check of such models. Now, the charges of the geometry, if you want, so the peculiarity here compared to the standard supersymmetric realization, as I said, is that these branes have non-trivial charges with respect to these tensor fields in the localized tensor fields, twisted fields. For example, you see here the charges of twisted charges of 9 branes. The ones of 5 branes have a factor of 4 bigger, and there are 2 kinds of 9 branes with positive and negative twisted charge. There are 2 kinds of anti-5 branes, positive and negative twisted charge, and the total number is fixed by, the total number of branes has to be 32 in my convention, 16 in the standard convention. And since in this model, the orientifolds have no twisted charges, so no twisted charges, if you want, the branes should adapt such that the twisted charges adapt to 0. So what you see here is the what are called untwisted tadpole cancellation, the total number of branes to be 32 or 16 depending on your convention. And here the couplings of the branes, you see opposite couplings of the 2 type of D9 branes, the opposite couplings of the 2 type of D5 branes should adapt to 0. In our example, we took the maximal gauge group, we put all the 5 anti-5 branes at one fixed point, let's call it the origin. And we did that, I believe most of the people are doing. We took the equal number of these D9 branes of 2 types, equal number of the anti-5 branes of 2 type. This led to the gauge group that I mentioned before, and also leads to the standard features that you can recombine these branes, which are called fractional, to move them in the bulk. Both D9 branes can be moved in the bulk or put Wilson lines. 5 branes can be moved by, you have to condense various scalars, condensing various, giving a vacuum expectation to various scalars. You start to move these objects into the bulk, if you want. And so these models have a lot of, if you want, moduli fields, so positions, if you want. And something which is well known in the standard supersymmetric example, but it's also true in these examples, is that if you give a vacuum expectation value to scalars in the bifundamental of D9 and D5, this has 2 interpretations. You can, Witten showed that you can understand 5 branes as gauge instantons on D9 branes. And this corresponds to some so-called charge 0 modes of the corresponding instantons. And you can also interpret, so you can interpret the 5 branes as instantons on D9 branes, or you can do something else. You can replace 5 branes with magnetic fields on D9 branes, and this would correspond to the limit in which the instanton has a kind of a maximal size. If you take an instanton, you take a kind of an infinite size, it becomes a dilute magnetic field if you want. And this you can understand. Now, this works always in all the supersymmetric examples. You can understand all the 5 branes like magnetic fields on D9. They're also called brane in branes. Or so it works also in all the in all these kind of supersymmetry breaking examples that we knew. Now, sorry, this I already showed, no? I showed it in the supersymmetric example before. I forgot. So this is I already showed. Okay, good. How comes? I know, but why? Like this? Because anyway, I'm not using. Okay. Sorry, Yeah, but I wonder now what I did. Okay, good. Okay, I think. I hope I didn't miss anything before. I think it's fine. No, I think it's fine. Okay, so what is the variation I'm talking about today? And Carlo again will continue. The variation is such that when you, again, you have to put in all these fixed points, the charge of the, since the orientifolds have no twisted charge, so these mirrors have no twisted charge, the branes should have 0 couplings also. And we always put the couplings of D9 branes to 0, the couplings of D5 branes to 0, and this was what we did before. There are solutions in which you cancel this local charge non-trivially between the D9 and D5 branes. So you just cancel non-trivially. For example, and actually there is a unique solution in this example in which you keep all the D9 branes together and you try to do something on the anti-5 branes, but such that this local twisted charge cancel non-trivially. Here, if you look a little bit here, in all fixed points, because D9 branes wrap the whole internal space, in all these 16 fixed points of the Z2, you have a difference of 20 minus 12 charge plus 8 coming from D9 branes. The 5 branes, these ones had the charge minus 4, and this one had a twisted charge plus 4. The only way to cancel this, and keeping the fact that the total number of branes is 32 here, 32 here, is to put 2 branes, 2 anti-5 branes of charge minus 4, if you want, in each fixed point. So we have to distribute them really 1 per fixed point, and this is the unique solution. You cannot do anything else in this case. Now, the outcome of this is that the anti-5 branes will have no positions. They are completely rigid, and this you can understand in various ways. First of all, in this case, the gauge group is USP2, and if you look at from the 5 branes, the gauge group of the 5 branes is USP2, and if you look at the spectrums, they have no scalar which can positions which can move around. You need some scalars which you can give a VEF to move these objects. They cannot move. The gauge group of D9 branes is this one, SO20 times SO2. I told you about the twisted charges. It's the unique configuration in which the cancellation is non-trivial. And again, if you look at the spectrum, there are no positions for anti-5 branes. No movable positions of 5 branes. But you cannot, in the BSB, you could recombine fractional branes to go in the bulk. Here you cannot. They are really stuck there, modulo something which I'll tell you later. Now, some of the D9 branes you can move. There are 20 D9 branes with positive charge, 12 of opposite charge. You can move 12 of them, 12 and 12 in the bulk. This you can do. But 8 of them have to stay there to cancel the charge of the anti-5 branes. That's all we can do. So what's the advantage in quatortion marks? It depends if you like it or not. There are less open string moduli. You have fewer open string moduli here compared to the usual case. And these solutions are not connected by continuous deformation with the other one. They are not. They are really disconnected if you want moduli space. Now there are some, so again, you can move, as I said, 12 of these D9 branes compatible with this charge conservation, and 8 of them have to stay there. I'm afraid that I'm again going, yes, in the wrong direction. Now, some puzzles, and then I will finish. As I said, in all the examples we know supersymmetric and even non-supersymmetric, you could understand D5 branes as gauge instantaneous D9 branes. This was the paper of Witten, and it's, as far as we know, it's always the case. Maybe not a posteriori, but this is the case I was always familiar. Or you could understand D5 branes, as I said, as constant magnetic fields on D9 branes. You could also understand this because the D9 brane with the magnetic field has the same charge as the D9 and D5. And this can be understood, as I said, by condensing these massless scalars. In our class of models, some of these scalars do not exist. And you can understand the result I'm going to talk about here also from other points of view. So there are some scalars, 9-5 scalars, between this SO20 and this USP2 anti-5 branes at the fixed points. You can give some VEV to this, so you can magnetize part of the D9 branes. So the SO72 factor, you can put magnetic field, not on the SO12. So these are models in which there are some gauge groups. You cannot put magnetic fields on some part of the gauge group. You cannot. There are no corresponding scalars there. Equivalently, if you look at these condensations from the field theory point of view, you cannot remove and replace all the D5, but it's the same thing. Anti-5 branes, if you want, you cannot all of them convert into instantons or magnetic fields. You can see it from the field theory point of view. Some of them have to remain in the spectrum. So it's the first examples I know, and a posteriori, I don't know if it's really completely shocking. You cannot understand 5 branes as either magnetic fields or instantons. In this case, however, using a T-dual language, in a non-perturbative way, even if you don't have the corresponding deformations, if you take all the branes and if you use the language of intersecting branes, you can take the sum of all of them, and it corresponds to so-called bulk cycles. So you could, in principle, recombine everything, but not in a perturbative way. But even this step here is not always possible. Carlo will give you an example, a more complicated example, still in 6 dimensions, and he'll make some comments about 4 dimension in which at the non-perturbative level, the branes are truly rigid. Some branes are truly rigid, even non-perturbative, you cannot recombine. You just cannot. And maybe the last comment and go to the conclusions. There could be an interest in these models, novel or not. I mean, by the way, if you know, maybe not in this context, but in general, other construction of this type, please let us know, not to forget to cite people. This is still work in progress, it's not yet published. In the standard brane breaking case, you generate only this called untwisted tadpoles, which means you have this total tension of anti-branes and antifolds, which add up, as you see here. Whereas in our case, and this was our original motivation to start this project, we wanted to break supersymmetry again on the brane, but not from this untwisted, but from a twisted perspective. We didn't succeed to get rid of this untwisted or unlocalized charge, if you want. But we have examples in our case in which you have both this untwisted potential, tadpole, and something coming in all these fixed points. And this could have an interesting consequence, first of all, from the point of view of this classical solution, stability that various people here, and Jihad will tell us more tomorrow, are investigating. These are different kind of models from this point of view. And also because maybe the dynamics can trigger these twisted scalars to take a wave. And actually, I call them twisted scalar. Yeah, because these are never short, yeah. And this could eventually remove the singularities. So-called blow up the orbifolds, maybe in a dynamical way. So this could be interesting also from this point of view, these models. So these are conclusions. Brane supersymmetry breaking in general provides various puzzles for single constructions. There is no order parameter for SUSY breaking. It's truly non-linearly realized, really in the original Volkov-Vakulov way. So these models are really explicit realization of Volkov-Vakulov kind constructions. Is difficult to understand in the simplest examples. How do you go from this to supersymmetry vacua? You know, the folklore that all the non-supersymmetric vacua and string theory are related in some way to supersymmetric one. In this case, even in the original construction, it's not obvious. We had some various speculation with Carlo, but it's not completely obvious. Ground state, of course, and Jihad will tell us much more about this tomorrow. And we worked out variant constructions which have additional puzzles, rigid branes, some of them you cannot move at all, 5 branes which are unrelated either by instantons or by magnetic fields to the 9 branes, and also we have additional scalar potential in the theory which can have different consequences for dynamics of the models. And you'll hear more from Carlo in the following talk about, for example, the defects, the lower dimensional effects like D1 branes, if you want, have also peculiar features here which I'll not discuss. And he will tell you something about a model which is truly rigid for some 5 branes. Even non-perturbatively, they are really completely rigid there. So this could be helpful for open string model stabilization. Thank you very much.
Thank you. Questions?
Yes, please.
These 6-dimensional models have anomalies. Yes, and I mean.
Well, it's
yeah,
but they cancel in the usual
exactly, yeah, but then they have to meet some conditions.
Yeah.
The question is if these conditions are related to the tadpole cancellation, or you have more, or you have less.
Absolutely. There is this anomaly polynomial, and you can work out the anomaly polynomial. You can factorize in the usual way. You understand it has to do with.
But I mean, there are no more, say, that they are one-to-one.
Yes.
Because I remember Uranga, Aldazabal, they had some cases where there were, I mean, I don't remember, but I think it was.
You mean if they are stronger, tadpoles are stronger than. Yeah, sometimes the tadpole Ramarwan tadpoles are stronger than anomaly cancellation. That's true, yeah. But in this, I mean, the anomaly cancellation works in the standard way. It's interesting indeed, but there is nothing puzzling. They are completely standard construction from this point of view. It's just this rigidity of objects because you are cancelling charges with 2 different kinds of objects which are not the same and generate this peculiarity and puzzles that I described.
More questions?
A quick question. Do we have to understand this rigidity of branes as a freezing of kind of freezing mechanism for branes? Or?
Yeah. Yes.
Okay, so it's the same mechanism as the freezing.
Yeah.
Okay, so maybe in a dual language, maybe Carlo.
Well, so the things which were certainly discussed several times in intersecting branes with various angles.
Yes.
This cancellation, non-trivial cancellation, is certainly at work there. But here we have standard branes, if you want, orthogonal branes.
Mm-hmm.
So it's different, but if you start to put angles, then for sure in all these intersecting branes, there are similar kind of constructions. But then these are different constructions.
Yeah, but yes, it is puzzling that you say that you cannot interpret the D5 branes as instantons.
This is at least, it seems a puzzle. to me. I don't know if it's completely shocking, but it's a fact, yes. Yes. Absolutely. Yeah. So again, it adds more to this peculiarity of these constructions. I mean, sometimes you can understand from field theory language. In some examples, you can understand that the gauge group just don't match. I mean, if you have SO for D5 and SO for D9, they cannot be instantons one of the other. You need to flip from SO to ESP, for example. You can understand it sometimes in these terms, yeah. But why? It's a good question. And again, from the point of view of magnetic fields, what does it mean that we cannot put magnetic fields sometimes?
Okay. Since we have to be sharp, let's thank Emilian again. And the next speaker is Carlo ANGELANTONJ from Torino. We'll talk about variations again on brane supersymmetry breaking.
Se me la mette, guardi, alla parte opposta, a sinistra, perché di solito a destra sono piene di trasparenza, vabbè. Okay, grazie. So I will start also, like all of us, to thank Augusto for having put up this nice meeting, and also for all the efforts, all the he put in the print in this program and try to bring it to a success, I think. So this talk is the second part of variations on brane supersymmetry breaking. You just heard the first part, and it's based on some work in progress, as Emilian said, with Emilian, Cesar, and Giorgio, and hopefully will appear soon. So you told me something wrong because I have to rotate. No. Okay, now it's working. Okay, thank you. The two actions are complicated, but why are complicated for the pointer, but maybe not for the vacua? And the natural question that actually I asked myself a long time ago is, why do you want to restrict one's attention to Z2 orbitals? After all, we know that there are many other possibilities, and we already know that in 4 dimensions, actually interesting chiral vacua can be built, but they involve a complex orbifold action, like the Z3 or more complicated. So we started playing, because I mean, just with the Zn orbifolds, and then generic. And since we are interested in 6-dimensional vacua, the options, the available options, if you want to keep a supersymmetry in the bulk, are just n equal to 2, which already was studied a long time ago, and Emilian reported upon it, n equal to 3, 4, and 6. These are the only consistent orbifold actions you can have on a T4, which give you a K3 compactification. Now, according to the definition of brane supersymmetry breaking that Emilian just gave you before, which is you must involve different kinds of orientable planes which have opposite charges and tensions, which forces upon you the breaking of supersymmetry. Then n equal to 3 case is not much interesting because n equal to 3 only has 9 planes, so at most you can play the game of Sugimoto, and indeed at the same orbifold, the same clustering vacuum you can attach 2 freely. I mean, it's up to you to choose which, if you want to attach a supersymmetric D-brane spectrum or a non-supersymmetric one. So n equal to 3 we are not considering, and the other 2 cases, 4 and 6, instead are interesting. It's the main, I will focus on them, and in particular on the Z4, because the Z6 shares most of the properties of the Z2 orbifold that Emilian just talked about. It's just a bit more complicated, but there are no news. So let me start with, I'm pressing the wrong button, with the Z4, and just a little bit on the geometry of the Z4 orbifold, T4 over Z4, which I need later on in order to understand what's happening in this kind of orientable vacuum. So you have the standard Z4 orbifold, and I take, for instance, the case where the T4 factorizes as the product of T tutori, and then the element of Z4, the generator of Z4, simply acts as a pi over 2 90 degrees rotation on the complex coordinate for each Z2. Actually, one should rotate clockwise and the other anti-clockwise, but actually this is a choice, is a definition. Now, the important things on an orbifold when you are on this singular space is counting the number of fixed points. And again, it's a simple exercise to see how many fixed points you have in each sector. And here you have different twisted sectors. And in particular, for the G and G cube twisted sector, you have the Z4 orbitals emit 4 fixed points, which are precisely, if you like, the origin of each T2 and the central point of each T2. So that when you rotate modulo identification of the lattice, you go back to the original space, to the original point. And the Z2, the G twisted. What am I doing? No, I'm going too far. Okay, the G squared, simpler, okay, I think I will go. G squared twisted sector instead is slightly more complicated because G squared is a Z2 action. So in principle, if you just want to list which are the fixed points of G squared, then you find the canonical 16 fixed points of a Z2 orbifold. But then you have to see how these Z2 fixed points are arranged into how they transform under the Z4 action. And then what you realize, again, is that the green and yellow ones are the Z2 fixed points, but the yellows are also coincide with the Z4 fixed points that I had before, whereas the green ones, and okay, you have to take, of course, the product. I mean, these are four-dimensional points in four-dimensional spaces, are actually transformed one to each other by the Z4 action, and therefore they form a doublet of Z4. So altogether in the G squared twisted sector, you have 4 Z4 fixed points and 6 doublets of Z2 fixed points. Okay, so just this is something which is well known, but just to recap and to fix some points. Okay. So now, if you consider the compactification of type 2b, which is what we are going to do on this orbifold, this is very well known, and you want to have a geometric action of the Z4 orbifold, which means that you rotate the left mover and the right mover coordinates by the same amount of e to the 90 degrees and not in opposite ways. Then, and this is also important for what follows for the construction, the torus partition function is of a charge conjugation type, the modular invariant, which means that for instance, the one twisted sector couples to the right movers to the G cube twisted sectors, and so on. And from here you can see which are the excitations, and then which are the light states. I mean, never mind, I mean, just for completeness, you build up the unique 6-dimensional vacuum with n equal to 2,0 supersymmetry, which indeed comprises a supergravity multiplet coupled to 20 tensor multiplets, out of which 3 come from the untwisted sector, and the remaining 18 ones come from the various twisted sectors, okay? So this is all standard, and now we want to play the game of building up, starting from the type 2b superstrings with the orientable projection to build some orientable vacua, or maybe hopefully of new type. So, and what we are interested in, we want to construct models with brane supersymmetry breaking. So borrowing from the original idea of Ignatius, Emilian, and Augusto, what we do, we combine the worldsheet parity actions, so omega, which exchange the left and right movers, with some inner automorphism which acts as on the internal space, which flips, the twisted homology of the K3 of the orbifold. So this means that the Klein bottle now, which schematically involves some extra minus signs, you see the -4 and the -6. Of course, the Klein bottle only receives contribution from the G squared twisted sector, because otherwise the states are not left-right symmetric. And these minus signs are important and are crucial because now this object anti-symmetrize the Klein bottle, the Navier-Stokes vectors, and symmetrize the Ramond one, which implies that now the massless spectrum of the closed string sector comprises 1,0 supergravity, always in 6 dimensions, which is now coupled to 6 hypers and 15 tensor multiplets. And among these 15 tensor multiplets, some, precisely 10, the 4 plus 6, come from this G squared twisted sector, okay, because precisely of the minus sign. So you see that you have 15 tensors, which is larger than 9. And actually 9 somehow is the limit when you can have perturbative vacua which admit a supersymmetric solution. 9 tensor multiplets and 12 tensor multiplets actually can live without. I mean, the closing sector is completely consistent by itself. You don't need to add the branes. The spectrum is anomaly free. The tadpole can be cancelled, and the construction would involve an equal number of O plus and O minus planes, so that Ramond-Ramond charges and tensions cancel. But as you increase the number of tensors, automatically this brings you a positive contribution to the tadpole from the rentival planes, which then involve, as Emilian explained before, the introduction of anti-branes, which automatically then give you a non-supersymmetric spectrum. Okay. Now, at the non-perturbative level, in F-theory, there have been vacua which have been constructed, which involves more than tensor multiplets. But from the perturbative point of view, this is the story. This is what happens. Now, okay. So you want to cancel tadpoles. So in these models, okay. So this is the model I want to consider. The Z4 with this action of the orientive of the omega projection. Of course, here I'm just showing some of the terms in the amplitudes. And you want to cancel tadpoles. Now, because of this minus signs, this action, because you have a lot of tensor multiplets from the twisted sectors, the untwisted tadpole is in the Klein bottle, receives this contribution, and I apologize, there is 1 over square root of d6, not 1 over d6. Should be V4, actually. The volume of the internal 4-dimensional space, so double mistake. And from there, you read, as Emilian was saying, that the orientival 9 planes, for instance, in this game, have a negative tension and negative charge, whereas the O5 have positive tension and positive charge. That's why we call O5 planes. And this is identical to the Z2 case. So nothing changes, and the discussion can go on as Emilian's talk. However, in this case, there is a huge difference. And the big difference is realized on the fact that these orientival planes actually, they do carry a twisted charge. So Emilian stressed a lot in his previous talk that the orientival planes were neutral, didn't carry any twisted charge, just the D-brane carried twisted charge, and then you had to impose the mutual cancellation of twisted Ramond-Ramond charges between the branes. But here the orientival planes carry twisted charge, and something new happens in the construction. So why is this possible? Why can orientival planes or even branes carry a twisted charge? Well, this is possible because this extra inner automorphism that you put together with the omega projection now yields tensor multiplets from the G² fixed points. And as a result, as Emilian was saying, if you see which are, when in the Ramond-Ramond sector, which are the forms which are even or odd with respect to the orientival projection, the 2 form, which sits in the tensor multiplet, always comes with a non-dynamical 6-form top form in 6 dimensions. And since these objects come from the twisted sector, these tensor multiplets, then there are some twisted non-dynamical 6th form, which can then act as sources, can be sourced by the orientival planes and by the D-brane. So that's why you can have twisted charges. And so now the question is, okay, which orientival planes can carry this charge? Do they, all of them, carry the twisted charge, or only a part of them? And let's see where the orientival plane sits. So in this Z4 orbifold, so in the Z4 orbifold, the torus must be a square, because otherwise it's not invariant under the pi over 2 rotation. And therefore, the orientival planes coincide, the coordinate of the orientival planes are precisely the same as the coordinate of the fixed point. So for each fixed point, at least in the Z2 sector, in G² twisted sector, there is an orientival plane, which is the red dot. Now, however, if we want to talk about charges of this object, then the charges is a local statement, doesn't care about the global structure of the K3. And we know, this is a cheap way to see it, that we already know from Emiliano, from Emilian's talk, or from more general considerations, that the orientival planes which sit on the Z2 fixed points, which are the green one, are not charged, do not carry a twisted charge, okay? As a result, the only ones which do carry a twisted charge are the orientifold planes, and which are then fractional, which sit on the Z4 fixed points. So we have a localized twisted charge coming from this orientifold plane, which is just on the yellow points and not on the green ones, okay? And indeed, the Klein bottom, the twisted contribution to the Klein bottom in the cylindrical, in the transverse channel, is a sum of 4 contributions, each coming from the 4 different Z4 fixed points. So now you can add branes. So you add the D9 and D5, anti-D5 branes. They must be anti-D5 because you want to cancel the untwisted tadpole. And also they have to be fractional. They must carry a Ramond-Ramond charge, the twisted Ramond-Ramond charge, precisely because the orientifold planes have a charge. So you must cancel, and this tadpole has to be canceled locally. You cannot just cancel globally in the construction. So the tadpole conditions, if you add these branes, then read like these ones. So N1, N2, and M count the number of D9 branes of different types, which will support different gauge groups. And the Ds refer to the gauge groups on the anti-D5 branes. And as you see, you must, at least in this, you have to distribute them over the various fixed points, Z4 fixed points, precisely in order to cancel the tadpole. If you try to concentrate them on a single fixed point, then you run into trouble, you don't cancel the twisted tadpoles, and the model is anomalous. So these conditions, what is the point? If you combine them, these tell you automatically that the source, the tadpole for the twisted orientifold planes must be entirely canceled by the anti-D5 branes. And if you combine this twisted tadpole with the untwisted one, you see that these branes, there is only one solution to these equations, which is D1 plus D2 equal to 8. And actually, if you look at the charges of the G and G cube twisted sector, then the two must be the same. So it means that D1, you must put 4 plus 4 anti-D5 branes on each Z4 fixed points, otherwise the model, the vacuum is inconsistent. So how am I doing with time? 5 minutes. So this is the spectrum of light excitations. This is the gauge group, and the gauge group, then you have an SO8 squared times U8 on the D9, and then on each Z4 fixed points where there are these anti-D5 branes, which cancel locally the twisted charge of the orientifold planes, you have a USP4 cross USP4. So for each of the Z4 fixed points. You have left-handed fermions, which are in the adjoint representation of the D9 group, so that you have, in a quotation mark, supersymmetry on the D9 branes, and they are in the antisymmetric representation of each USP4, so you have a lot of gauginos, potential gauginos in there, so that the construction is consistent. But then you see that you have, let's concentrate just on the scalars, you can have indeed hypermultiplets for on the D9s, which are in these bifundamental representations, and also some real scalars, which are in this bifundamental representation between, and that's, I will comment about it later, between the unitary gauge group, which lives on the D9, and the various symplectic gauge groups which are associated to the anti-D5 branes. So you don't see, again, here you don't see moduli for fields, moduli associated to the position of the anti-D5s, which cannot be moved around at all, okay? And, okay, these are the scalars. I forgot to highlight this slide. You can see, the fact that these D branes cannot be moved, you can see both from cannot freely be moved in the bulk. You can see from the spectrum, from the field theory analysis, you cannot condense any scalar which would give you, would allow you to move partially these branes in the bulk. And indeed, you have to cancel tadpoles, so if you start to move them, then in principle you run into trouble and you have an anomalous spectrum. A quick comment about defects on these branes. So you can add also defects, one-dimensional defects, because you have two forms in the spectrum. You have tensor multiplets, so tensor multiplets can be sourced by D1 branes, which live in 6 dimensions. And this D1 brane can be either D1 branes in 6 dimensions, or can be what we call D5 prime branes, which are D5 branes which wrap the T4 mod Z4, which wrap the internal space and therefore are two-dimensional from the space-time point of view. And you can see that, okay, you can work out the spectrum, and actually these are the gauge group which live on the branes, and we worked out also the various charge and uncharged moduli. Now, the anomaly is completely cancelled for this model. There is a generalized Green-Schwarz mechanism a la Sagnotti, and the anomaly in the bulk, there is an anomaly inflow on the various defects, which is cancelled by the unitary theory which lives on the defects, so the model is completely consistent, at least for perturbative case, and then would be maybe interesting to repeat the analysis of Ivano for these more general Diefried anomalies for these models, but I think it's, I don't know, it's doable or not, you will tell us in the future. Now, as Emilian mentioned, again, the interpretation of Witten of branes as instantons of the higher dimensional objects, again, seems to fail completely, because you cannot see any, I mean, you can see the D5 prime branes as instanton of the D9. That's fine, because they have the right gauge group, USP for the SO and unitary for unitary, and you find all the excitations. But you cannot see the D5, the anti-D5 of the bulk as instanton of the D9, or the D1 as instanton of the anti-D5. And the simple way to see it is, okay, supposedly you could say, okay, the USP gauge group is the gauge group which would live on the instant of an SO gauge theory. However, if I look at the spectrum, the charge moduli, and I have to go backward like this, the charge moduli, which would go between the instanton and the would be gauge theories, now are charged with respect to unitary gauge group, are not charged with respect to the SO gauge group as you would expect. So there is no interpretation of this anti-D5 as, at least we couldn't work it out, as instantons of the D9. And also, it seems that it's complicated to magnetize, or impossible to magnetize this object in order to dilute the D5 branes in the bulk, on the bulk, on the D9 ones. So just a last comment about the 4-dimensional models. You can repeat the same exercise. This is not something that exists only in 5 dimensions, but you can work also in in 6 dimensions, but also in 4. And in particular, if you take the Z2 cross Z2 construction with discrete torsion, then you have to introduce with this choice of particular choice of epsilon discrete torsion. This implies that you have to flip the orientival planes of one type. Here you have 3 different types of orientival 5 planes. For instance, the 053, which wraps the third torus, the 32, must have a positive tension, a positive charge. And these were the tadpole, the standard tadpoles for the models that we worked out a long time ago together with Augusto, Giuseppe D'Apollonio, Ignatius, and Emilian. And you have similar ones. And this, okay, is a standard, more conventional construction, which I'm not commenting about upon it. However, here also you can decide in these models, actually all the anti-D5 branes were localized on a single fixed point, so it was a simpler construction. But then if you start to move it around, since they also carry twisted charge, you cannot put, I mean, if you move a brane, you have to rearrange the whole configuration. And again, you get 4-dimensional vacua, which have a D9 gauge group, which with a gauge group which is U10 times U6, which with moduli that you can at least condense the U6 in the bulk. However, on the various D5 branes, the gauge groups that they don't admit, let's say, scalars in just representations of the U1 or the USP 16, and they are completely frozen. Okay. So I think, okay, in the Z4 model, Emilian showed you a case where you have extra contribution to the energy effective actions. Actually, in Z6, for this kind of models, you have a lot of contribution. You have a lot of new terms in the potential. We scale differently with the various twisted moduli and with the internal components of the metric, if you like, which are localized on the T2, which are localized in various dimensions. There are several contributions which can make the dynamics of this vacua richer and maybe definitely more difficult to study, I believe, because you have a much more complicated potential in this case. So this brings to my conclusion. So sometimes looking elsewhere can bring some new surprises. And then there are a lot of open questions which are connected to brane recombination in these models. It's not clear whether they, I should mention brane recombination in quotation mark, are these connected by magnetized deformation? Because when you work on Zn orbitals, they are not anymore T-dual to, magnetic fields are not T-dual to brane recombinations anymore. You change completely the internal space. How can it be reconciled if it should be reconciled with the instanton picture? And then what is the dynamics of these states? So I think I stop here and thank you very much.
Thank you.
Yeah, Carlo and Emilian, thank you very much for this talk. I'm a bit puzzled why this is a puzzle, actually. So if I think about of D-branes being classified by K-theory, which is also due to Witten, I mean, usually if you change the background, you have to consider a different K-theory. So if you, for instance, change from type 2, this is the picture you usually have, D9, and then turning on gauge field, you get D5 brane, say to type 1, where you just do an ordinary orientifold projection. You also get new kind of stable branes, the non-BPS branes, for instance, which you cannot see in your former theory. I think here probably something very similar is just happening. You have a new orientifold projection. Of course, it's not clear what kind of K-theory you have to compute to implement maybe this extra action in the Klein model that you have. But I wouldn't be surprised that you find new things.
The surprise is that the same orientifold projection, depending on how you distribute, how you play with your game, they do admit an interpretation in terms of instantons and so on. The original model of ADS, Antoniadis, Dudas, Sagnotti, on brane supersymmetry breakings, the anti-5 branes, they do admit an interpretation in terms of instantons of the D9. But if I start to move them around, then I lose the interpretation. So it's not a new background, it's not a new twist, it's not a new whatever. No, it's that, these are the same branes, but they cancel charge differently.
Maybe it's this is my suggestion. Maybe it's a new kind of D5 brane that do not have any deformations. You can move them away from the fixed points.
I don't know. I don't see, but I understand your.
It's just a new thing.
Could be, but to me they look very much the same. Simply they are distributed around. But maybe I'm wrong.
So maybe related to this or alternative to this, actually this question was asked before, but I didn't understand the answer. So in the previous talk. So what if you T-dualize twice? Because maybe sometimes mysterious properties become.
I go from, in the Z2, you can do. The Z2 is a real action. So it's no problem. You rotate by 180 degrees, so there is no problem. And indeed, if you T-dualize twice, you can have a picture of all this construction that we made in terms of intersecting branes wrapping cycles, and there you can understand, in fact, at the non-perturbed, you might, maybe all these vacua are reconnected by moving all the branes in the bulk. However, in this Z4 case, if I T-dualize, then I go from a geometric T4, mod Z4, to a non-geometric one, because if I T-dualize, I introduce T-duality means x right goes to minus x right, so when I rotate, I'm not rotating anymore x left and x right by the same angle, but I rotate them by opposite angles. And now opposite angles for 180 degrees is the same. At opposite angles for 90 degrees, or Z6, whatever you want, it's completely different. So the intersecting brane pictures cannot, the intersecting brane picture that the vacua that Ralph and his students, collaborators have worked out in 6 dimensions, actually they are intersecting brane models of a different kind of geometry, starting from type 2A compactified on that orbifold, which is not the same as the type 2B on this.
So, sorry, to summarize this, if you TDLize this becomes non-geometric.
Becomes non-geometric,
so, okay.
which
you
I don't know then what is a geometric,
it gets even worse.
Yeah.
So I was wondering about these new contributions to the tadpole potential due to the twisted moduli. So if you express everything in canonically normalized fields, do you only get exponentials, or do you also get like monomials times exponentials or other things?
Depends on the fields. So you get exponentials in the dilaton because these are disk or cross-cup contributions, so they have exponential e to the minus phi in the canonical, let's say, in the string base. But then, well, the dependence on the twist fields, I don't know. I mean, one should work out. I mean, it would be a linear term plus maybe other sort of couplings, and this we didn't work out. You have to compute the amplitude and see what it gives you. I cannot answer to that. But there are various combinations, and 4 dimensions will be various combinations of fields which involve some twist fields from different sectors which enter into the potential now. The potential is not just e to the minus phi times square root of g. That's definitely not the case. It's dressed with other fields and with other...
It's not a question, but a really minor comment, is that for 4-dimensional orbifolds, if you are going to break supersymmetry, then there is also a set 5. There is not, there's
yes,
one more.
That's true.
Okay,
okay, but we want to keep supersymmetry in the bulk. So the brane supersymmetry, the whole game of brane supersymmetry, I fully agree with you, because if you want to break supersymmetry, you can start considering any kind of orbifolds. You are not forced to take 3, 4, 6, whatever, 7, and so on and so forth. You have more choices. But these orbifolds break supersymmetry already at the level of the closed strings. And normally these orbifolds, these non-supersymmetric orbifolds, they bring you tachyons into the game, already at the closed string sector. So we wanted to be, first we wanted to play the game of brane supersymmetry breaking, which means a supersymmetric bulk coupled to a non-supersymmetric open string sector. And second, when you start playing with the non-supersymmetric orbifolds, normally, in my experience, I mean, I don't have a theorem, but I work out a lot of models for fun on my notebook, you get a lot of tadpoles.
Okay. Let's thank Carlo again. Now there is a break. We reconvene sharply at 5.